Hello everyone, I'm Jong-Seok Lee from Yonsei University in Korea. Today I'd like to present our work on dynamic thresholding for learning sparse neural networks. This is a work done by my student Jin-Woo Park and myself. In these days, we witness significant advances in the deep neural network architectures. The trend is that the network complexity is getting higher and higher to increase the capability of the networks. However, when you consider constrained environments like embedded systems or mobile systems, high complexity is not desirable, and there is a need for small but efficient network architectures. There are several approaches to resolve the issue of the network complexity. One is neural architecture search to find a new efficient architecture automatically. We can also use knowledge distillation, where a less complex student model learns the capability of a more complex teacher model. Another approach is to obtain sparse neural networks through pruning. In this case, starting from a trained network, redundant weights or neurons are removed to reduce the complexity. In this work, we focus on the third approach because of some advantages, like we can use known qualified architectures, and pruning often brings large amounts of complexity reduction, and it is also relatively easy to implement. The way pruning works is like this. We repeatedly remove some weights or neurons and retrain the whole network, and this repeats again and again. However, this is a significant computational burden. So our first research question is how to reduce this kind of trial and errors. Then another problem is that the threshold for pruning is not easy to determine. So our second research question is how to automatically determine the pruning threshold. So in this work, we proposed the so-called dynamic thresholding approach to learn sparse neural networks by training both weights and thresholds without trial and errors. The basic idea of the proposed method is to combine a loss term that is related to threshold parameters in the final loss function, like in this equation. Here, W means the weight and T is the threshold. So the goal is to find the weight and threshold parameter at the same time by minimizing two terms. One is the conventional loss function, for example, cross entropy in classification, and the second one is the new pruning loss term. So we have two problems. One is that the pruning function that returns 0 if the weight is smaller than the threshold is not differentiable. And second, the pruning loss function need to be defined in an appropriate way. So for the first issue, so we call the original hard pruning function as hard pruning function, and it is shown in the graph as a black line. So it has two continuities, so it is not differentiable. So for training, we replace this one with the so-called soft pruning function using error functions, and it becomes differentiable. So we use the soft pruning function for training, but we use the hard pruning function for inference. Then the second issue is how to define the sparsity-promoting loss term. So we take by following many previous works, we also consider that the small weights can be removed from the network. So basically, we want to increase the threshold value so that more weights can be pruned and the network complexity is decreased. So we define the pruning loss as a negative logarithm of the threshold. So at the end, the final loss function for training is given by the equation at the bottom. So it's a combination of conventional loss term like cross entropy minus some parameter lambda and logarithm of the threshold. Let's have a look at how our method works. So here are the equations for weight and threshold updates using gradient descent method. So the difference of the two equations is in the last part, the gradient of the soft pruning function with respect to the weight and threshold. If we write them down, then we can find out that the derivative with respect to the weight is always positive, and the derivative with respect to the threshold has the opposite sign to the sign of the weight. So based on this, we can have a look at what happens actually. So let's consider the weight is positive. And let's say the weight was larger than the threshold at the beginning, and the weight updates reduces the weight value. The threshold will then increase based on the previous slide, and eventually the weight can be pruned in the, as shown in the figure. Well, the opposite also can happen. Let's say the weight was smaller than the threshold, so it was pruned, but it is updated to become larger. Then the threshold will become smaller, so the weight can be recovered back, where we have a situation of splicing. So this shows that the weights in our method can be dynamically pruned and spliced during the training. Here's a toy example of training a simple two-layer network for the XO problem. These graphs show how each weight and the corresponding threshold evolve during the training. Here the weight is represented by blue lines and the threshold is represented by red lines, and the shaded regions indicate that the weight is smaller than the threshold, so the pruning is the weight is removed. If we take an example of this case, well, at the beginning the weight was larger than the threshold, so it is connected, but the weight becomes smaller at some point, so it is pruned, and then the weight becomes larger than the threshold and it's spliced again till the end of the training. Next, we evaluate the proposed method on 3 classification problems, including MNIST, Cypher10, and ImageNet. And we tried different architectures like LUNET and VGG and AlexNet, and we compare our method with these kinds of different previous approaches. So the result is shown here. We show the accuracy loss and the compression ratio for each cases. So as you can see here, our method achieved the best compression ratio marked with red color for Cypher10, and then the second best performance for MNIST and ImageNet. So we can say that our method shows competitive compression ratio compared to the other method for various problems and network architectures. Here's the summary. So we have proposed a dynamic thresholding to obtain pruned neural networks without necessity of trial and errors, and also manual pruning threshold selection. The proposed method trains the threshold parameters with gradient descent optimization, and it is able to dynamically prune and splice weights during training, and the experiments show that it can produce good performance in terms of accuracy and compression ratio reliably across different networks and datasets. Thank you very much.